Hello and welcome to the Learn English Lab. Today's podcast, well, it's an English listening practice podcast, and our topic is 40 plus C1 level vocabulary on science. And we're doing a deep dive today, embarking on what I think is a pretty exhilarating journey, actually. We're getting into the very language that truly unlocks the universe around us. Yeah, we've curated over 40 C1 level scientific vocabulary terms. So if your goal is maybe mastering complex scientific discussions, for studies or work, or maybe just because you're curious, then you are absolutely in the right place. Think of this deep dive as maybe your direct path, a way to become really well-informed and articulate when you're navigating this fascinating world of science.
It's so true. And what's really compelling about this kind of specialized vocabulary, it's power, not just for advanced English learners, though definitely for them, but really for anyone who wants a, let's say, deeper grasp to scientific concepts. These aren't just like dusty words in textbooks. They're the actual tools you need. Tools for dissecting complex scientific articles, for engaging in sophisticated debates about the latest breakthroughs, and even for just genuinely appreciating popular science stuff with a richer, more nuanced understanding. When you really command these terms, you're not just memorizing definitions, you're significantly boosting your ability to articulate complex ideas. And you can do it with, remarkable clarity and real confidence.
That really hits home the value there. And our mission for this particular deep dive is pretty clear, I think. We want to extract the most impactful insights from this powerful set of words. We're going to systematically break down these essential terms, offer you some alternative ways to say things, really broaden your vocabulary, and vividly show how they're used in different scientific contexts. And sometimes, even in surprisingly everyday situations. Our promise is to fill your mind with some really memorable details and those deeply satisfying aha moments, the kind that make learning feel not just easy, but genuinely engaging. We're here to make understanding the cutting edge of science not just, possible, but actually enjoyable for you, making you well-informed and ready to, apply this knowledge. All right, let's dive right in. We'll kick things off by delving into the really foundational elements, the sort of unseen powers and building blocks that fundamentally shape our whole universe. We'll explore the particles that make up everything we see and the forces that bind them and move them around. And where else could we possibly begin but with the term that gets right to the heart of all matter? Atomic candy. So when we talk about something being atomic, what do we mean? We're referring to anything related to atoms. Now, atoms, they're the smallest, most fundamental units of matter. And our understanding covers their, intricate structure, their unique characteristics, and crucially, how they interact, how they connect with each other. It really is the starting point for almost all scientific investigation. That's a great way to put it, yeah. And when we think atomic, other words might pop up, like nuclear or subatomic, maybe elemental. But what's truly profound here is that the atom, it isn't just like one component among many. It's the absolute bedrock, the foundation for all scientific understanding. Without a decent conceptual grasp of the atom, it's basically impossible to fully get chemistry or a lot of physics or even biology at its most fundamental level, the molecular stuff. It sounds, I suppose, like a relatively simple idea on the surface, but its discovery must have been, world-changing. How did atomic theory revolutionize chemistry by explaining how elements combine? What was so profound about that?
Oh, it genuinely was a seismic shift, a huge change. It marked a transition from, what was largely just observational chemistry, almost like alchemy in a way, to a truly predictive science, something you could actually test and verify. Before atomic theory, scientists could describe reactions, sure, but they didn't really have a coherent framework for why they happened. The big conceptual breakthrough was proposing that matter is made of these discrete, indivisible units, atoms, right? And that these atoms combine in fixed, simple ratios. That idea completely transformed how we understood matter and chemical reactions. It gave us the intellectual scaffolding, the structure to predict the properties of compounds and understand the stoichiometry of reactions, how much of what reacts with what. That really paved the way for modern chemistry as we know it today. It shifted the focus from just seeing things happen
to actually understanding the rules underneath it all.
Exactly, to explanation and prediction, which is, fundamental to scientific progress.
Yeah. So it moved science forward significantly. And this isn't just history, is it? Researchers are still pushing these boundaries. I'm really intrigued by this idea that researchers study atomic vibrations to develop new materials. What does that actually mean in practical terms? How does fiddling with something so tiny create something useful?
It's a fantastic illustration, actually, of how understanding the minuscule, the incredibly small, can lead to huge macroscopic breakthroughs. By studying and manipulating the incredibly subtle vibrations of atoms within a material structure, its lattice, scientists can essentially engineer materials right at their most fundamental level. Imagine developing alloys that are not just stronger and lighter, but maybe also resistant to extreme heat, or semiconductors that are way more efficient for electronics.
Wow, so real-world applications.
For sure. We're talking about creating materials that might even self-repair if they get damaged, or maybe conduct electricity with zero resistance at room temperature. That's a huge goal. It's a direct path from unlocking the secrets of atomic motion to creating innovations with immense practical value across countless industries, aerospace, medicine, fundamentally altering the properties of matter itself.
That's amazing, from these invisible little wiggles of atoms to things that could genuinely change our lives, and maybe on a more everyday scale, something we might just take for granted. Atomic clocks provide highly accurate timekeeping for global navigation systems. How does that connect back to atomic properties, and why is that kind of super accuracy so vital?
Well, this really exemplifies how profound fundamental science underpins our most advanced societal systems. Our infrastructure, atomic clocks. They don't just tell time, they kind of redefine it. They measure time based on the incredibly stable and consistent oscillations, the vibrations, of certain atoms like cesium or rubidium. They achieve an accuracy so high they wouldn't gain or lose a second in, hundreds of millions of years.
That's just staggering precision.
It is. And it's far from just an academic curiosity. It's the invisible force that synchronizes global communication networks, keeps financial transactions secure, and crucially, provides the super precise timing signals that let GPS satellites pinpoint your location on Earth with, astonishing accuracy. So the humble atom, with its incredibly stable, predictable vibrations, it isn't just a building block of matter, it's the invisible timekeeper for global systems, commerce, navigation, quietly powering the intricate synchronization of our modern world.
That really is an aha moment, realizing that without that atomic level stuff, our digital world just wouldn't function.
Spot on. It makes you realize that what seems abstract is often incredibly practical.
Yeah, and the pursuit of just fundamental knowledge can have these totally unforeseen benefits. Amazing. Okay, moving from the atom as a whole to its very core. Let's look at nucleus now. In biology, this is defined as the part of a cell that contains most of the genetic information.
That's right. And you could think of synonyms like cell core, maybe genetic center, or even chromatin hub. The nucleus plays such a central role in cellular life because it's essentially the command center. It's in charge. It safeguards and organizes the cell's genetic material, the DNA, right? And that DNA then dictates almost everything the cell does. Its structure, its functions, how it reproduces. It really is the ultimate control room.
Okay, so for instance, a key function is that the nucleus directs protein synthesis through DNA transcription. Could you maybe unpack that core function a bit more? Why is it so vital for life?
Absolutely. This is a core function in molecular biology, no doubt, and it's central to how life keeps going. Inside the nucleus, the DNA holds the intricate instructions for making all the proteins a cell needs to function. Transcription is the process where a specific gene's DNA sequence gets copied into a messenger RNA molecule, an mRNA. This RNA then travels out of the nucleus into the cell's main body, the cytoplasm, and it guides the process of building proteins. This whole intricate, highly regulated process governs all cellular functions, from providing structural bits to catalyzing chemical reactions with enzymes. It effectively makes the nucleus the ultimate conductor of life's essential processes. Any disruption here, it can have huge knock-on effects.
So what happens if that command center gets compromised? You said it's so crucial. How does damage to the nucleus can impair cell division processes actually play out? What are the bigger implications?
Well, this has profound and often really devastating health implications. If the nucleus, with all its carefully organized genetic information, suffers damage maybe from radiation, certain chemicals, or even just errors during normal cell processes, then cells might lose the ability to divide correctly. Or maybe they can't divide at all. This can lead to a whole range of serious issues, from slowing down tissue repair and regeneration to, more seriously, contributing to uncontrolled cell growth, proliferation, which is, a hallmark of cancer.
I see.
So maintaining the integrity and the healthy function of the nucleus is absolutely paramount, both for individual cell well-being and for preventing many diseases. It's why cells actually have these elaborate repair mechanisms specifically for the DNA inside the nucleus.
So understanding its vulnerability is just as important as understanding its function.
Yeah.
That makes sense. And how do we even know all this? We're talking about something microscopic, right? Microscopes reveal the nucleus as a distinct organelle in eukaryotic cells. How did just seeing it pave the way for deeper understanding?
Yeah, this really underscores the sheer importance of observational science and also technological advancement. The development of increasingly powerful microscopes, especially electron microscopes, allowed scientists to really peer into the microscopic world of cells. With unprecedented clarity, seeing the nucleus as a distinct, organized thing, an organelle separate from the cytoplasm and containing its own internal structures like the nucleolus and chromatin, that was a major discovery.
It wasn't just a random blob inside the cell.
Not at all. It was an organized component. And this visual identification was the first step. It enabled scientists to then figure out its composition, its role in heredity, and all its various functions through later biochemical and genetic studies. It's a real testament to how advancing our tools, our ways of observing, directly leads to breakthroughs in our fundamental understanding of life.
It really does highlight that even the most complex biology often starts with just careful observation. The nucleus, this tiny command center, profoundly influencing life, death, and disease at the cellular level. It shows that the blueprints of life are both intricate and, well, quite delicate. Okay, now, let's talk about the connections between those atoms we started with. Bond. A bond is a link that holds atoms or ions together in any molecule or crystal.
Right. Synonyms could be chemical link, molecular tie, or maybe atomic connection. These links are quite literally the glue holding the material world together. They dictate how stable substances are, what their properties will be like, melting point, boiling point, conductivity, and importantly, how they react with other compounds. Understanding chemical bonds is absolutely foundational to understanding all matter.
Okay, a prime example and a really fundamental concept in chemistry. Covalent bonds share electrons between atoms for stability. Can you explain what's happening with the electrons here? Why is sharing so important?
This is basic chemistry, but incredibly important. Atoms, generally speaking, are kind of aiming for stability, right? They typically want a full outer shell of electrons. In a covalent bond, atoms achieve this stability by sharing one or more pairs of electrons between them. This mutual sharing creates a strong, directed link, forming molecules like water, H2O, or carbon dioxide, CO2. Understanding this electron behavior is absolutely key to grasping the structure, the shapes, and the reactivity of countless compounds, both organic and inorganic. It essentially defines the rules for how molecules are built. It's like a tiny, extremely strong handshake between atoms.
A handshake, I like that.
Right.
And for something tangible, we all know, which involves a very different kind of bond. Ionic bonds form crystals like table salt through charge attraction. How does this differ from the sharing in covalent bonds?
Ah, yes. This is a perfect illustration of how these fundamental atomic connections lead to visible macroscopic structures, things we see every day. In an ionic bond, the electron situation is quite different. Instead of sharing, one atom actually transfers an electron completely to another atom. This creates oppositely charged ions, one positive and one negative.
Okay, so one gives, one takes.
That's it. And these ions then strongly attract each other because of their opposite charges, like tiny magnets. They form a rigid, repeating three-dimensional structure called a crystal lattice, like the familiar cubic structure of sodium chloride, which is just common table salt. It's the powerful electrostatic pull between these charged ions that creates such strong, stable compounds.
Okay, and here's a biological twist, showing maybe the more delicate side of these connections. Breaking hydrogen bonds denatures proteins in high heat. This sounds pretty critical for biological function.
Oh, absolutely. This takes us into biochemistry and is critical for understanding how temperature affects complex biological molecules like proteins, hydrogen bonds. They're much weaker attractions between molecules or between different parts of a single large molecule. They aren't the strong bonds within atoms. Collectively, though, lots of these weak bonds play a crucial role. They maintain the specific three-dimensional shape of proteins, and that shape is essential for their biological function, what they do.
So the shape is everything for a protein.
Pretty much. And when proteins, like the ones in an egg white, for example, are exposed to high heat, these delicate hydrogen bonds break. This causes the protein to unfold or denature. It loses its specific shape and, as a result, its biological function. That's exactly why cooking an egg changes its texture so dramatically and irreversibly. The proteins have denatured. It shows this delicate balance that allows life to function, which is vulnerable to environmental changes like heat.
It's amazing how these chemical bonds, from the incredibly strong covalent and ionic ones to the surprisingly delicate hydrogen bonds, dictate everything. from the salt on our tables to the very structure of life itself. Understanding these atomic connections is truly like seeing the fundamental architecture of our world. Okay, from the very small scale of bonds, let's zoom out to the incredibly vast. Let's talk about gravity. This is defined as physics, the universal force of attraction between any pair of objects with mass.
Right. You could use synonyms like gravitational pull, attraction force, or maybe weight inducer. Gravity's influence is truly pervasive, everywhere. From holding us firmly on the Earth to shaping the largest structures in the cosmos, it's one of the four fundamental forces of nature, and arguably the one we experience most directly every single day.
And this force governs our whole cosmic neighborhood, right? As in, gravity keeps planets in orbit around stars. Can you explain how that works on such a grand scale?
Yeah, this is perhaps the most iconic example of gravity's power. It's like the invisible hand that sculpts the large-scale structure of the universe. Without gravity, planets would just fly off into space, in straight lines, following whatever path they started on. Instead, the immense mutual attraction between a star, like our sun, and its planets causes the planets to continuously fall around the star. They follow these predictable elliptical paths. It's a perpetual dance of attraction and motion that keeps solar systems and galaxies stable.
A delicate balance, it sounds like.
It is. If the force were too weak, planets would escape, too strong, and they'd crash into the star. It's finely tuned.
But gravity isn't just about planets way out there. It affects us directly, profoundly, especially when we leave Earth. Reduced gravity in space affects human bone density. Why is our body so dependent on this constant pull?
That's a really critical area of research, especially for space exploration and long trips in space. On Earth, our bones are constantly remodeling themselves, getting stronger in response to the continuous load and stress put on them by gravity. Just standing up, walking around. In the microgravity environment of space, that essential stimulus, that stress, is largely missing. Without that regular loading, the body starts to resorb bone tissue, brace it down. This leads to a significant loss of bone density over time and also muscle atrophy, muscle wasting.
Wow.
Yeah, it really highlights the profound physiological impact of being off Earth. It shows how our bodies, having evolved here, are just meticulously adapted to our planet's specific gravity. Astronauts have to do really rigorous exercise routines in orbit to try and combat this.
And back here on Earth, understanding gravity is fundamental for safety and the structures we build all around us. Engineers account for gravity in bridge designs for stability. How crucial is this understanding for actually constructing our modern world?
Oh, absolutely indispensable. In structural engineering, understanding gravity isn't just important, it's the bedrock principle, the absolute foundation. Every bridge, every skyscraper, every single structure we design and build must be meticulously engineered to withstand that relentless, omnipresent downward pull of gravity. Engineers perform complex calculations to make sure the materials they choose, and the design itself, can safely distribute those forces across the whole structure. This guarantees the stability, the durability, and the safety that are essential for, well, public confidence, and of course, for preventing catastrophic failures. It's a constant, unwavering force that demands unwavering respect in construction.
Gravity. From orchestrating these celestial dances to subtly shaping our bones and firmly grounding our buildings, it truly reminds us of the fundamental forces governing everything, from the macro to the micro, and mastering it is essential for both discovery and just daily life. All right, our final term in this first section is particle. In physics, this refers to any of the smallest units that energy or matter consists of, such as electrons, atoms, molecules, etc.
Right. Synonyms could be subatomic unit, quantum entity, or maybe matter fragment. What's interesting about this term is its broad scope. It covers such diverse scales of matter and energy, from the incredibly tiny quarks and neutrinos all the way up to larger atoms and even molecules. It's a really versatile word for describing the fundamental bits of everything in the universe, regardless of their specific nature or size.
Okay, so to see particles in action at an extreme level, particle accelerators smash atoms to discover new elements. What does this actually tell us about the composition of matter? What are we learning?
This really describes the cutting edge of high-energy physics research. Scientists use these massive, complex machines, particle accelerators, like the Large Hadron Collider at CERN, to propel subatomic particles, often protons or electrons, to incredible speeds, nearly the speed of light. And then they collide them, smash them together. By carefully observing the fleeting debris from these incredibly powerful collisions, they can probe the deepest secrets of matter. They can even create entirely new, unstable elements that only exist for fractions of a second, or discover previously unknown fundamental particles.
Wow. It sounds like controlled chaos.
It kind of is. It's like smashing two watches together at immense speed to figure out all the tiny gears and springs inside. It helps us understand the fundamental forces governing the universe and ultimately the building blocks of reality.
And for something beautiful and much more common, an everyday example, air particles scatter light, creating blue skies. How do these tiny particles manage to paint the whole sky blue?
This is a wonderful connection between fundamental physics and just looking up. It's an atmospheric optics phenomenon. It's called Rayleigh scattering. Basically, the tiny nitrogen and oxygen particles, the molecules in the atmosphere, are actually quite small compared to the wavelengths of visible light. They scatter shorter, bluer wavelengths of sunlight more effectively than the longer, redder wavelengths, and they scatter it in all directions.
Okay.
So this scattered blue light reaches our eyes from all over the sky, making the sky appear blue. Now, at sunrise or sunset, sunlight has to travel through much more atmosphere to reach us. Most of the blue light gets scattered away before it gets to our eyes, allowing the longer, redder wavelengths to pass directly through. That's why we get those stunning orange and red sunsets and sunrises.
That's fascinating. A simple, elegant demonstration of particles interacting with light energy.
Exactly.
Now, for something really mind-bending, taking us deep into the quantum realm, quantum particles exhibit wave-particle duality. This seems to challenge our basic understanding of how things should work.
Oh, it absolutely does. This takes us deep into theoretical physics, and it's genuinely one of the most intriguing, counterintuitive, and profound concepts in modern science. At the quantum level, particles like electrons or photons, they don't behave strictly as either distinct particles, like tiny billiard balls, or as continuous waves, like ripples on a pond. Instead, they exhibit characteristics of both, depending entirely on how they are observed or measured.
So how we look at them changes what they are.
In a way, yes. This duality really challenges our classical intuition because we expect things to be definitively one or the other, a wave or a particle. It suggests that observation itself isn't passive. It plays an active role in shaping reality at the subatomic scale. It's a concept that still sparks intense debate among physicists about the fundamental nature of existence and measurement. It's a real aha moment that shows how the rules of our everyday world just completely break down at the smallest scales.
What an incredible journey through just these first few terms. From the invisible dance of atomic particles to the grand cosmic pull of gravity. These terms really are the vocabulary of cosmic understanding. All right, so we've laid some groundwork with the fundamental physics and chemistry of the universe. Impressive stuff. Now let's pivot to the equally fascinating vocabulary of life sciences. Let's cover the intricate processes of evolution, genetics, and how biological systems actually function to create and sustain life. And we'll start with the engine that keeps all living things going. Metabolism. Metabolism is defined as the chemical processes through which food is changed into energy for the body to use. It's basically the sum total of all the chemical reactions happening in an organism, keeping it alive, right?
That's a great definition. Spot on. You could also use terms like biochemical conversion or energy processing, or you could refer to its two main sort of opposing components. Catabolism, that's the breaking down of molecules to release energy, and anabolism, which is the building up of complex molecules from simpler ones, and that requires energy. Metabolism really is the dynamic engine of life within all organisms, from the simplest bacteria right up to complex humans. It's how we sustain ourselves, grow, repair damage, and respond to our environment.
Okay, and many people immediately connect this term to, personal health goals, like weight loss, for instance. High metabolism aids in rapid weight loss with exercise. How does our individual metabolic rate influence our body weight and energy use?
That's a very common connection people make, and there's a significant truth to it. An individual's metabolic rate, basically, the speed at which their body converts food into energy and burns calories, does indeed influence weight management. People with a naturally higher basal metabolic rate, that's the energy they burn just resting, or maybe those who boost it through regular exercise, they will typically use up energy more rapidly. And that can potentially lead to quicker weight loss or make it easier to maintain weight. This interplay really highlights the individual differences in how we use and store energy. It emphasizes that understanding your own unique metabolism is a key part of, personalized health and fitness strategies.
They're not the same for everyone.
Not at all. It's a complex symphony of biochemical reactions influenced by genetics, age, gender, activity levels, lots of factors.
So what's actually happening at the micro level to regulate all these complex processes? Enzymes regulate metabolism and cellular reactions. Can you explain the role of these biological catalysts?
Sure. This delves into the incredibly precise and orchestrated biochemical machinery working inside every single cell. Enzymes are specialized proteins that act as biological catalysts. What that means is they dramatically speed up or regulate the huge array of chemical reactions that make up metabolism. Without enzymes, these intricate cellular reactions, everything from breaking down glucose for energy to synthesizing new proteins, would just happen far too slowly to sustain life.
They're like tiny accelerators.
You could think of it that way. They act like molecular machines, making sure that metabolic pathways run efficiently at the right speed and under the correct conditions. It really illustrates the intricate, finely tuned dance of molecules that keeps us alive and functioning smoothly. They are truly the unsung heroes of our internal chemistry.
And thinking about a medical context where things can sometimes go wrong, thyroid disorders disrupt normal metabolism rates. What role do hormones play in keeping this delicate balance?
Yes, this connects directly to medical conditions and really underscores the critical role hormones play in maintaining metabolic balance throughout the body. The thyroid gland, which is in your neck, produces hormones, mainly thyroxine. And these hormones have a profound influence on nearly every cell's metabolic rate, how fast it works. So if the thyroid is overactive, that's hyperthyroidism. Metabolism speeds way up. This leads to symptoms like weight loss, rapid heart rate, anxiety. Conversely, if it's underactive hypothyroidism, metabolism slows right down, resulting in weight gain, fatigue, feeling cold.
That throws everything off balance.
Completely. It clearly shows just how central metabolism is to our overall physiological well-being and how its delicate balance is tightly regulated by our endocrine system, our hormone system.
So metabolism isn't just about weight. It's the fundamental energy exchange that defines life. A complex, enzyme-driven engine regulated by hormones, keeping every organism going. Okay, next up, we have a real cornerstone of all biology, evolution, and its adjective form, evolutionary. Evolution is, biology, the slow and gradual development of living things throughout the history of the Earth. And evolutionary means related to evolution, or the slow and gradual development of something.
That's it. For evolution, synonyms might include species development, adaptation process, or even Darwinian change. And for evolutionary, you could say developmental, adaptive, or progressive. This theory is genuinely the unifying framework for all of biology. It explains the incredible diversity of life we see on Earth, how species change over vast periods of time, and why organisms often seem so remarkably well suited to their particular environments.
We can literally see this history written in the rocks, can't we? Fossil records document evolution over millennia. What can fossils actually tell us about the long journey of life?
Oh, the evidence from paleontology, from studying fossils, is utterly compelling. It provides a direct chronological sequence of life forms throughout Earth's history. Fossils show us how species have changed, diversified, and adapted over millions, even billions of years. They illustrate the critical transitions between different groups of organisms like, for example, the evolution of whales from land-dwelling mammals, or birds evolving from feathered dinosaurs.
Those transitional fossils are amazing.
They really are. They offer concrete clues to our own origins and the evolutionary pathways of ancient life. It's like finding missing pages from Earth's autobiography, Each fossil is a snapshot of a past era, showing the gradual unfolding of biodiversity over time.
And it's not just ancient history, is it? Evolution is happening right now, with really significant consequences for us. Antibiotic resistance shows evolution in bacteria. How does this very modern example of evolution impact human health so directly?
This is a powerful and unfortunately very immediate example of evolution in action, with critical implications for modern medicine. When populations of bacteria are exposed to antibiotics, those individual bacteria that just happen to have pre-existing genetic mutations making them resistant to the drug, they survive, while the non-resistant ones die off. These resistant survivors then reproduce, passing on their advantageous genes. Over time, sometimes quite quickly, These resistant strains become more and more common in the population. It demonstrates how evolution is a continuous, dynamic process that can dramatically impact public health and the effectiveness of our medical treatments.
It's a constant battle then.
It really is, a stark reminder that we're in an ongoing evolutionary arms race with microorganisms.
Okay, so using the adjective form, what actually drives these changes? Evolutionary pressures favor survival traits. Can you elaborate a bit on what these pressures are and how they sort of sculpt species over time?
Sure. This explains the core mechanics of natural selection, which is the main engine driving evolution. Evolutionary pressures are basically environmental factors, things like predators, competition for limited food or water, changes in climate, diseases, even finding mates, anything that challenges a species' survival and reproduction. Individuals within a population who happen to possess traits that better enable them to survive and reproduce despite these specific pressures, well, they're more likely to pass on their genes to the next generation. This process, happening over countless generations, systematically shapes the characteristics of species. It leads to adaptations that optimize them for their particular environment.
So it's not like individuals are trying to evolve.
Not at all. It's about differential survival and reproduction based on the inherent variation that already exists within a population. Some just happen to be better equipped for the current conditions.
Evolution. Truly the grand narrative of life, explaining both the breathtaking diversity and the intricate adaptations we see everywhere, from ancient fossils to modern drug resistance. It reminds us that life is constantly changing, shaped by these relentless pressures of survival. Okay, from that broad sweep of evolution, let's zoom right in to the instruction manual of life itself. Genome. This is the complete set of genetic material of any living thing.
You can absolutely think of it as the genetic blueprint, yes. Or the DNA sequence or the hereditary code. The genome is truly the comprehensive instruction manual for life. It contains all the information needed to build, maintain, and reproduce an organism. It's an incredibly complex and precise library of genetic information organized into structures called chromosomes, and it dictates everything from eye color to susceptibility to certain diseases. A huge achievement that really changed medicine was sequencing the human genome, advanced personalized medicine. How did that massive project fundamentally alter our approach to health?
Oh, that was a truly groundbreaking moment in scientific history, a landmark in genomic research. By mapping the entire human genome, decoding the complete sequence of DNA-based pairs, scientists gained an unprecedented, holistic understanding of our genetic makeup. This vast knowledge is now foundational for what we call personalized medicine, where treatments and preventative strategies can be meticulously tailored to an individual's unique genetic profile.
So not just treating everyone the same way.
Exactly. Instead of a one-size-fits-all approach, doctors can now better predict how someone might respond to a certain drug, assess their risk for certain diseases more accurately, and design therapies that are potentially far more effective for specific patients based on their genes. It's really revolutionizing drug development and disease prevention by moving from general treatments to incredibly precise, genetically informed interventions.
And it's not just medicine, right? It's changing our food supply too.
Yeah.
Plant genomes are edited for crop improvement. What are the implications of this kind of biotechnology for feeding the world?
Yeah, this connects directly to the exciting and rapidly advancing field of biotechnology and agriculture. By precisely editing the genomes of plants using powerful tools like CRISPR, scientists can introduce desirable traits. Things like increased yield, better resistance to pests or diseases, improved nutritional value like vitamin-enriched rice, for example, or maybe greater tolerance to environmental stresses like drought or salty soil.
That sounds incredibly useful.
It holds immense potential, yes, for improving food security globally, making agriculture more sustainable, and enhancing the quality of the food we grow. It's a powerful tool for tackling some of humanity's most pressing challenges related to food production.
What about looking backwards? Tracing ancestry and understanding our place in the big tree of life. Comparative genomes reveal evolutionary relationships. How do scientists use this genetic information to connect different species?
This highlights its profound utility in what's called phylogenetic studies, tracing the evolutionary history and relationships of species. By comparing the entire genomes of different organisms, everything from bacteria to humans, scientists can identify shared genetic sequences, track mutations that have occurred over time, and pinpoint differences that have accumulated over millions of years. This allows them to construct detailed evolutionary trees, illuminating the deep genetic connections and the points where different species diverge.
Like a family tree for all life.
Pretty much. It provides concrete evidence of common ancestry and shows how life has diversified across the planet. It's like using a massive genetic library to read the history of life and understand our own biological heritage.
The genome, truly the instruction manual of life, a testament to nature's incredible complexity and precision. From tailoring individual medical treatments to enhancing global food supplies and tracing our evolutionary past, it's a field just brimming with both profound insights and huge potential for shaping our future. Now, sometimes that genetic instruction manual gets a little typo, a mistake, and that brings us to mutation. This is biology, a change in the structure of the genes of an individual that causes them to develop different physical features.
Right. Synonyms could include genetic alteration, variant, or maybe anomaly. Mutations are the fundamental source of genetic variation, and that variation is the raw material that evolution works on. They are essentially random changes in the DNA sequence. They can arise spontaneously during DNA replication, or they can be induced by external factors like radiation or certain chemicals. These changes can have a whole range of effects, sometimes no noticeable change at all, sometimes subtle alterations, or even profound structural, functional transformations.
And while we often associate mutations with negative outcomes, sometimes these typos are actually a good thing, aren't they? Beneficial mutations enhance species survival. Can you explain how these random changes can actually drive adaptation?
That's a crucial concept in evolutionary biology, yes. While it's true that many mutations are neutral, meaning they have no effect or even harmful, occasionally a random change in the genetic code can actually provide an evolutionary advantage in a specific environment. For example, a mutation might happen to confer resistance to a new disease, or enable an organism to better utilize a new food source, or maybe improve its camouflage to avoid predators.
So a lucky accident, basically.
You could say that. Such a beneficial mutation increases an individual's chances of surviving and reproducing. This allows it to pass on that advantageous gene to its offspring, thereby driving adaptation and change within the species over generations. It's a powerful illustration of how random events can lead to directional evolution.
But there are also clear external factors that cause mutations, aren't there? UV radiation induces DNA mutations in skin cells. What's happening at the molecular level there? And what are the real-world risks?
Yes, this explains a very common environmental cause of genetic changes and highlights some significant real-world risks. Ultraviolet UV radiation from the sun carries enough energy to directly damage DNA molecules in our skin cells. This damage can lead to errors when the DNA is copied or repaired, resulting in mutations. These accumulated mutations can disrupt normal cellular function, particularly the genes that control cell growth and division. Which is precisely why prolonged and unprotected exposure to sunlight is a major risk factor for various forms of skin cancer. It's a direct link between an environmental agent, UV radiation, genetic alteration, mutation, and disease cancer.
And tragically, this idea of accumulated errors relates to a major health concern globally. Cancer often results from accumulated mutations. How do these genetic changes lead to such a devastating disease?
This connects mutation directly to pathology, the study of disease. Cancer isn't typically caused by just one single isolated mutation. It's usually the result of a series of accumulated genetic errors that happen over time within a cell's DNA. These mutations can disrupt the normal regulatory mechanisms that control cell growth, division, and even programmed cell death, apoptosis. When multiple key genes that regulate these critical processes get mutated, cells can start to proliferate uncontrollably. They divide when they shouldn't. They can invade surrounding tissues and even spread to distant parts of the body, forming cancerous tumors.
And these mutations can be inherited or acquired?
Both. Some mutations can be inherited from parents, increasing predisposition, but more commonly they are acquired throughout life due to environmental factors, lifestyle choices, or just random errors during DNA replication. Understanding these specific mutations is absolutely key to developing new, targeted cancer therapies that attack the specific weaknesses of cancer cells.
So mutations, they're the engines of both evolution and disease.
Yeah.
A testament to the powerful, sometimes unpredictable impact of tiny changes in our genetic code. They remind us of the constant interplay between randomness, our environment, and the precise machinery of life. Okay, our final term for this section on life sciences is clone. This is a cell or a group of cells created through a natural or artificial process from a source that they are genetically identical to.
Right. You could also use terms like duplicate, replica, or genetic copy. The core concept here is genetic replication, whether it happens naturally, like in some plants or bacteria through asexual reproduction or through artificial laboratory techniques. It means creating an organism or a cell that is an exact genetic match to another one, carrying the identical set of genes.
The most famous example, which really blew people's minds at the time, is surely cloning sheep like Dolly Advanced Biotechnology. What were the big scientific implications of that landmark experiment?
Oh, Dolly the sheep, born back in 1996. She was indeed a monumental achievement, a true landmark experiment in biology. She was the very first mammal cloned from an adult somatic cell that's a regular, non-reproductive body cell. This success pushed the scientific boundaries immensely. It demonstrated that adult cells, which are specialized, could actually be reprogrammed back to an embryonic state and then develop into a complete viable organism.
That must have opened up a lot of possibility.
It really did. It had huge scientific implications, catalyzing significant research into both reproductive cloning, creating a whole organism, and perhaps more importantly, therapeutic cloning. Therapeutic cloning focuses on creating embryonic stem cells for medical research cells that could potentially treat diseases without actually creating a full organism. Dolly completely reshaped the field of biotechnology and our understanding of cell differentiation and potential.
Beyond the big headlines, cloning also has very practical agricultural uses, doesn't it? Plant clones ensure uniform crop characteristics. How does this benefit farming?
Yes, this is a very common and beneficial practice in horticulture and agriculture. Many desirable plant varieties, maybe a fruit tree that consistently produces the sweetest apples, or a potato strain that's resistant to a particular disease, are propagated using cloning methods, like taking cuttings or using tissue culture in a lab. This ensures that all the new plants are genetically identical to the parent plant. That guarantees uniform characteristics like consistent fruit quality, predictable disease resistance, the same flowering time, and overall predictable yield.
So reliability for the farmer.
Exactly. This genetic consistency is invaluable for commercial agriculture. It ensures reliability and quality for consumers, too.
But the whole idea of cloning, especially when you start talking about humans, raises some profound ethical questions. Ethical debates surround human cloning possibilities. What are some of the key concerns that arise from this powerful technology?
Absolutely. This is where scientific advancement really intersects deeply with moral and societal considerations. While therapeutic cloning, which involves creating embryonic stem cells for research to potentially treat diseases like Parkinson's or diabetes, is widely researched and generally seen as less controversial, reproductive human cloning, creating a genetically identical human baby, remains highly contentious, extremely controversial. The ethical debates revolve around really fundamental questions of individuality, human dignity, the potential for exploitation of clones, and also profound safety concerns about the health and normal development of any cloned individuals. The process is still very inefficient and risky.
Serious questions to grapple with.
Indeed. These discussions encourage critical thinking about the responsible application of scientific capabilities, the limits we choose to place on technology, and really what it means to be human in an age where we have this level of advanced genetic manipulation potential. It's a complex discussion with no easy answers.
From the groundbreaking creation of Dolly to the tricky ethical dilemmas of human replication, cloning really showcases how scientific capability can often outpace our societal readiness to deal with it. It's a powerful reminder that progress also demands thoughtful reflection on its implications. Okay, we've journeyed from the subatomic realm right through the intricate dance of life itself. Now let's transition to our final segment. We'll cover a broad spectrum of terms related to materials, chemical reactions, energy, and even some more abstract scientific concepts that help us interact with and describe the physical world around us. Let's start with a substance known for its distinctive and often quite powerful properties: acid. Acid is defined as a water-soluble chemical substance that contains hydrogen and has a sour taste or corrosive feature with a pH less than 7. We encounter acids in everyday life and industry, from the relatively benign, like vinegar, to the quite dangerous.
That's right. Synonyms might include corrosive agent, proton donor, or sour compound. What's important here is its fundamental role in both chemistry and biology. Acids are essential reagents, starting materials in countless chemical processes, and their property of readily donating protons, hydrogen ions, makes them highly reactive and crucial for many natural systems. The pH scale, remember, goes from 0 to 14, measuring acidity or alkalinity, with 7 being neutral. Anything below 7 is acidic.
And remarkably, our own bodies use powerful acids. Stomach acid aids digestion of proteins. How does our physiology manage to safely utilize such a corrosive substance for essential processes?
It's a great example of biological engineering, really. The hydrochloric acid, HCl, in our stomachs creates a highly acidic environment, a pH typically between 1.5 and 3.5. Very acidic. This extreme acidity is vital for two main things. First, it denatures proteins. It unfolds their complex structure, so digestive enzymes can then chop them up more easily into smaller bits. Second, it kills most bacteria and other pathogens that we might swallow with our food, so it's a crucial defense mechanism.
But how does it not digest the stomach itself?
Good question. Our stomach lining is protected by a thick layer of mucus and also by carbonate, which acts as a buffer against the acid. This prevents self-digestion. It's quite an elegant solution to a dangerous necessity.
Beyond biology, acids are absolutely key to technology. They power so much of our portable world. Battery acid powers electrical devices. What's its function in energy storage?
This connects directly to industrial applications and a core component of modern energy storage technology. In many common lead-acid batteries, like the ones in most cars, sulfuric acid acts as the electrolyte. The electrolyte is the medium that allows ions, charged particles, to move between the battery's positive and negative plates. This movement facilitates the chemical reactions that generate electrical current.
So the acid enables the electricity flow.
In essence, yes. During discharge, when the battery is providing power, the acid reacts with the lead plates. During recharging, the process is reversed. So, understanding the precise properties and concentration of acids is fundamental to designing, optimizing, and ensuring the safety and efficiency of these batteries that power countless aspects of our modern lives.
And unfortunately, acids also have a significant negative environmental impact globally. Acid rain damages ecosystems. How do human activities contribute to this? And what are the consequences?
Yes. This explores the broader, often detrimental consequences of chemical processes on our planet, directly linked to human industrial activity. Acid rain forms when gaseous pollutants like sulfur dioxide and nitrogen oxides, which are primarily emitted from burning fossil fuels in power plants and vehicles, react with water, oxygen, and other chemicals up in the atmosphere. They react to form sulfuric acid and nitric acid. These acids then fall back to Earth, mixed in with rain, fog, snow, or even as dry particles.
And the damage.
It can be severe. Acid rain can harm forests by leaching essential nutrients from the soil. It can acidify lakes and rivers, leading to fish kills and harming aquatic life. It also accelerates the decay of buildings, statues, and infrastructure made of stone or metal. It tragically emphasizes the interconnectedness of atmospheric chemistry, industrial output, and delicate ecological health. A powerful warning about environmental responsibility.
Acids, from their life-sustaining role in our stomachs to powering our cars and, sadly, damaging our environment. They really demonstrate the incredible versatility and impactful presence of fundamental chemical compounds, a force to be reckoned with, both beneficial and destructive. Okay, from corrosive agents, let's move to facilitators of energy and flow. Let's look at conductor. This is a substance that permits electricity to pass through or along it.
Right. You could use transmitter, pathway, or current carrier as synonyms. This term describes a fundamental concept in physics conductivity, which is the ability of a material to allow the flow of either electric charge or heat. Materials vary hugely in their conductivity. It's determined by their atomic structure and how many free-moving electrons they have available. This property dictates their suitability for an enormous range of different applications, everything from electrical wiring to cooking pans.
And we encounter excellent conductors constantly in daily life. Metals are excellent conductors of heat. Why are they so good at transferring thermal energy? What makes them special?
This highlights their unique thermal properties, which are directly related to their atomic structure. Metals possess what's often called a sea of delocalized electrons. These are electrons that are not bound tightly to any single atom. They're free to move throughout the entire piece of metal. These free electrons are highly efficient at transferring kinetic energy, which is what heat is at the atomic level from one part of the metal to another.
So they carry the heat energy along.
Exactly. When one end of a metal object is heated, these electrons quickly absorb that energy and rapidly transmit it throughout the material. That's why a metal pot heats up quickly on the stove, or why a metal spoon left in hot soup becomes warm almost instantly. It's all about how efficiently materials can transfer energy.
And for a truly amazing feat of physics, something that seems almost magical, superconductors eliminate resistance at low temperatures. What's the profound implication of this phenomena? What could it allow us to do?
This delves into an advanced and genuinely fascinating phenomenon rooted in quantum physics. Superconductors are a special class of materials that, when you cool them below a certain critical temperature, often extremely low, close to absolute zero, they lose all electrical resistance. Zero resistance.
All of it.
All of it. This means an electrical current can flow through them indefinitely without any energy loss as heat. Unlike conventional conductors like copper wire, where some energy is always lost due to resistance, this has revolutionary potential for things like energy transmission. Imagine sending electricity across vast distances with zero waste. Or for creating incredibly powerful electromagnets used in high-speed maglev trains and medical imaging technologies like MRI machines, and even for advanced computing. It's a testament to the unexpected and powerful behaviors materials can exhibit under extreme conditions, challenging our everyday understanding of electricity.
And here's a fun one, a totally different kind of conductor that highlights how versatile language can be. Orchestral conductors lead musicians.
Yes, that's a great example of a metaphorical use. It shows how scientific terms can sometimes jump domains and enrich our everyday language. While an orchestral conductor isn't literally dealing with electrons or heat transfer, the underlying idea is similar, guiding and directing a flow. In this case, it's a flow of musical performance, making sure all the different elements are synchronized and working together harmoniously. It perfectly captures the essence of a conductor's role, enabling a complex system to function effectively.
From ensuring power flows seamlessly through wires to orchestrating a beautiful symphony, the concept of a conductor really underpins efficiency and coordination across incredibly diverse areas. It's about enabling flow, whether it's electrons or melodies. Okay, next, let's talk about how things release energy or particles out into their surroundings. To emit. This means to release heat, light, sound, radiation, etc.
Correct. Synonyms could include to discharge, to radiate, or simply to give off. This describes the active process of projection or release of energy or particles from some source, often out into the surrounding environment. It's a very active verb that applies across many scientific disciplines, describing the origins of everything from the glow of a distant star to the invisible signals coming from your phone right now.
Look up at the night sky, and you see this in action on the grandest possible scale. Stars emit light through nuclear fusion. This is literally the energy source of the entire cosmos, isn't it?
It absolutely is. This discusses a fundamental astronomical process and is indeed the very energy source that illuminates the universe. Stars are colossal nuclear furnaces. Inside them, under immense gravitational pressure and at incredibly high temperatures, lighter atomic nuclei, mainly hydrogen, fuse together to form heavier nuclei, like helium. This nuclear fusion process releases enormous amounts of energy in the form of light, heat, and other types of radiation.
And that's what we see as starlight.
That's exactly it. This process causes stars to literally emit the energy that makes them shine, which then travels across vast interstellar distances, sustaining planets, and ultimately making life possible in places like Earth. Without stellar emission, the universe would be a very cold, dark place indeed.
But there's also a significant downside when we talk about emissions from human industrial activity. Factories emit pollutants into the air. What are the environmental consequences of these kinds of emissions?
Yes, this connects directly to pressing environmental concerns and the impact of industrial processes on our planet. Industrial factories, in the course of manufacturing things and generating energy, often release unwanted byproducts, pollutants, into the atmosphere. These can include greenhouse gases like carbon dioxide, which trap heat. They can include particulate matter, tiny airborne particles that are bad for health, and various toxic chemical compounds too. These emissions contribute significantly to air pollution, they drive climate change, and they can have severe impacts on public health, causing respiratory diseases and also damaging ecosystems.
Because it's a major problem.
A critical one. It highlights the urgent need for sustainable practices and cleaner technologies to mitigate these detrimental effects.
And right now, as we're having this conversation, we're relying on things that emit signals to communicate and connect us. Devices emit signals for communication. How pervasive is this in our modern connected world?
Utterly pervasive. This illustrates its crucial role in technological function. Our modern world relies heavily on emitted signals for almost all forms of communication. Your smartphone emits radio waves to connect to cell towers. Your Wi-Fi router emits electromagnetic signals to connect your devices to the internet. Even your PV remote control emits infrared signals to change the channel. The ability of devices to generate and project these various forms of signals carrying information is fundamental to virtually all forms of wireless communication. It enables the instantaneous global connectivity that we often just take for granted. It's an invisible web of emitted energy all around us.
From the fiery heart of stars billions of miles away to the unseen signals connecting our devices right here, to emit describes the fundamental act of projection that drives both cosmic phenomena and our daily technological interactions. It's the mechanism of energetic communication. Staying with light, let's focus specifically on laser. This is a device that produces a powerful and concentrated beam of light that can be used in medical procedures for cutting metal objects, etc.
Right. You might sometimes hear it called coherent light or an amplified beam. Technically, LASER is an acronym, light amplification by stimulated emission of radiation. The really unique properties of laser light are what make it so versatile and powerful. It's highly coherent, meaning all the light waves are in phase, marching in step. It's monochromatic, meaning it's essentially a single color or wavelength. And it's highly collimated, meaning it travels in a narrow parallel beam without spreading out much.
So very different from a regular light bulb.
Very different. A regular bulb scatters light in all directions, all mixed wavelengths. A laser produces a very specific, very focused type of light.
And its precision is truly remarkable, especially in medicine. Lasers correct vision in eye surgeries. How does this focused light achieve such delicate medical procedures?
This details the incredible medical precision lasers offer, particularly in ophthalmology, eye surgery. In procedures like LASIK, highly focused laser beams are used to precisely reshape the cornea, the front surface of the eye. By ablating, which means removing tissue using light energy microscopic layers of corneal tissue, the laser corrects refractive errors. Things like nearsightedness, farsightedness, astigmatism. This allows light to focus correctly on the retina at the back of the eye. The laser's ability to deliver energy with such pinpoint accuracy and control lets surgeons perform these delicate, minimally invasive procedures that significantly improve patients' vision. It's an amazing application of light for healing.
And in heavy industrial settings, lasers are real powerhouses too. Industrial lasers cut precise metal parts. How has this technology revolutionized manufacturing?
This connects lasers to modern manufacturing efficiency and precision, definitely. High-power industrial lasers are capable of cutting through thick sheets of metal, welding components together with exceptional strength, and engraving intricate designs onto various materials with incredible speed and accuracy. They've revolutionized many production processes because they offer unparalleled precision, they create minimal material waste compared to some other methods, and they have the ability to work with complex shapes and geometries that traditional cutting tools just can't handle.
So faster and more accurate.
Generally, yes. From aerospace components to tiny microelectronics, industrial lasers are a cornerstone of advanced manufacturing today. They provide a non-contact, high-energy solution for processing materials.
And for something much more commonplace, something almost everyone has encountered, laser pointers aid presentations.
Smiles.
Yes, this points out its common everyday utility, doesn't it? Brings the concept much closer to home. While obviously far less dramatic or powerful than surgical or industrial lasers, the simple laser pointer uses the exact same fundamental principle, emitting a focused, narrow beam of coherent light. It just serves to draw attention to specific details on a screen or a board during a presentation. It proves that even a powerful scientific principle can be scaled down for widely accessible, practical, and effective communication. It's become a staple in classrooms and boardrooms everywhere.
From reshaping our vision to slicing through steel and even just guiding our attention in a lecture, the laser truly embodies the power of focused light. It's a technology that has profoundly impacted medicine, industry, and even our daily communication, showcasing the incredible potential when light is precisely controlled. Okay, moving now to something that defines the absence of matter, vacuum. This is a space that is utterly empty of all matter. Right. Synonyms could include void, emptiness, or pressureless space. Now, while a truly, utterly empty space without even a single particle is largely a theoretical ideal, we can create practical, very good approximations of a vacuum right here on Earth. And space itself, outer space, is a near-perfect natural example. The concept of a vacuum is crucial across physics and engineering, influencing everything from space travel to how we keep food fresh.
We even have devices that create vacuums right in our homes. Vacuum cleaners remove dust efficiently. How does this common household appliance actually work using the principles of a vacuum?
It's a great connection between the concept and a practical device. A vacuum cleaner works by creating a partial vacuum, basically, an area of significantly reduced air pressure inside the machine, usually using a motor-driven fan. This creates a pressure difference between the inside of the cleaner and the air in the surrounding room. The higher atmospheric pressure outside then pushes air, along with dust, dirt, and debris, into the lower pressure area inside the cleaner.
So it sucks things in because the outside pressure pushes them.
That's the principle. It's a simple yet incredibly effective application of creating low-pressure areas for a specific purpose. It shows how understanding air pressure can lead to clever cleaning solutions.
And on a much, much grander cosmic scale, that same basic principle applies. Space is a near-perfect vacuum. How does this definition shape our understanding of the universe beyond Earth?
Well, this describes its cosmic reality. While space isn't absolutely empty, there are still sparse particles of hydrogen gas, dust grains, cosmic rays whizzing around. The vast regions between stars and planets contain extremely small amounts of matter, incredibly low pressure. This makes it an excellent natural approximation of a vacuum, and this fundamental characteristic of space has profound implications. It's why sound cannot travel in space. There just aren't enough particles close together to transmit sound waves. It's why objects in space experience no air resistance. And it's why spacecraft need specialized, sealed life support systems for astronauts. It defines the environment in which stars, planets, and galaxies exist and interact.
And bringing it back to everyday life again for preserving our food. Vacuum sealing preserves food freshness. How does simply removing the air extend the shelf life of food products?
This illustrates its critical role in preservation methods. It leverages the properties of a vacuum or new vacuum to inhibit spoilage. By removing most of the air from a package before sealing it, vacuum sealing significantly reduces the amount of oxygen present. Oxygen is a major factor in food spoilage. It promotes oxidation, which is a chemical breakdown, and it also allows aerobic bacteria, molds, and yeasts, microbes that need oxygen to thrive and multiply.
So no oxygen, no spoilage.
It drastically slows it down. By reducing or eliminating oxygen, vacuum sealing effectively hinders microbial growth and slows down those chemical reactions that cause food to go stale, change color, or rot. This extends the shelf life of many food products considerably, keeping them fresher for longer.
The vacuum, defining an absence, yet it paradoxically empowers us in so many ways. From cleaning our homes to preserving our food, and even understanding the vast emptiness of space. Its power really lies in what it takes away, creating conditions that are otherwise impossible. Okay, finally, let's tackle a concept that really defies conventional boundaries and stretches our imagination. Infinite. This means without end or limits in extent, amount, or space.
Right. You could substitute terms like boundless, endless, or limitless. This discusses a concept that's abstract yet profoundly important. It has significant implications not just in science, but also in mathematics, philosophy, and even in our everyday language. It really pushes the limits of our comprehension, prompting us to consider what might lie beyond what we can perceive or count.
One of the grandest questions in science, a topic of constant debate and wonder, relates directly to this. The universe may be infinite in size. What does this cosmological theory actually entail for our understanding of reality?
This delves deep into cosmological theory and is truly one of the grandest questions human beings have ever asked. While we can only observe a finite portion of the universe, what we call the observable universe, limited by the speed of light and the age of the universe, theoretical models, especially those supported by observations about the universe's geometry, it appears flat, and the theory of cosmic inflation early on, these suggest that the entire universe could indeed be infinite in spatial extent. It might just go on forever in all directions, without any boundary or edge.
That's hard to grasp.
It is truly mind-bending. If true, it would mean there's an infinite amount of space, containing an infinite number of galaxies, stars, and potentially even exact copies of ourselves, our planet, everything, existing in distant, unobservable regions far beyond what we can ever see. It's a concept that really stretches our imagination to the breaking point and forces us to reconsider the sheer scale of reality.
In mathematics, though, infinity isn't just a philosophical idea, it's handled very precisely, isn't it? Infinite series converge in mathematics. How do mathematicians manage to grapple with an endless sum that somehow still yields a finite specific answer?
Yes, this connects the abstract concept of infinity to incredibly powerful analytical tools in mathematics. While an infinite series, by definition, has an endless number of terms that you keep adding together. Some of these series can actually converge. That means the sum gets closer and closer to a specific finite value as you add more terms, and it never goes past that value. For instance, the series 12 plus 14 plus 18 plus 116 and so on. You keep adding smaller and smaller fractions. The sum approaches 1, but it never actually reaches or exceeds 1, even with infinite terms.
So you can tame infinity, in a way.
In certain contexts, yes. This is a profound idea. It shows how mathematicians have developed sophisticated tools and rigorous proofs to precisely manage and understand situations involving endlessness. It demonstrates that even infinity can sometimes be quantified and understood in specific, well-defined ways. It's a real triumph of logic over simple intuition.
And just like we saw with conductor, we often use this powerful word metaphorically in everyday life, too. His patience seemed infinite with children.
That chuckles softly. Indeed. This highlights the metaphorical use perfectly. It shows how scientific and abstract terms can beautifully enrich our everyday language, making our descriptions more vivid and impactful. While, of course, literal human patience isn't truly infinite, using the word conveys this impression of an inexhaustible, boundless supply. It emphasizes the remarkable extent of that quality in someone. It speaks to the power of language to extend meaning beyond its technical origins and resonate deeply with human experience.
And there you have it, a truly expansive and, we hope, thoroughly engaging deep dive into these powerful C1 level science vocabulary terms. We've journeyed from the tiniest atomic bonds all the way out to the boundless reaches of the infinite universe, exploring the precise language that allows us to understand, describe, and interact with the world around us.
What's truly fascinating here, I think, is how these seemingly disparate scientific terms, from atoms and genes to gravity and light, actually form a coherent, interconnected tapestry. Each word is like a thread, helping us unravel the universe's immense complexities and articulate its wonders. And this raises an important question, perhaps. How does our continuously evolving scientific vocabulary not only reflect what we currently understand, but also actively shape our future discoveries and even our very perception of reality? The words we choose can genuinely open entirely new avenues of thought and research.
That's a powerful thought to leave you with indeed. Thank you so much for joining us on this deep dive. We truly hope you feel more articulate, informed, and maybe inspired, ready to integrate these powerful terms into your own discussions and understanding. Keep questioning the world. Keep exploring the wonders of science through words, because the journey of learning is, well, practically infinite. We really hope you liked this deep dive.
Definitely hope it was useful.
And if you did, please remember to like, share, and subscribe to the Learn English Lab YouTube channel. We really appreciate your support.